Okay.
Good
So
afternoon, sir.
good afternoon. Good afternoon, Srinivasan. So what I'm going to do is because I wanted to have a practical class, but
Yes,
since
sir.
it is not, we can't do it now. So I want to do it in person. So what I thought was I will explain, especially with Arjun there, and to certain extent, Jason also may understand this. Uh,
Yes, sir.
so I want to explain the our glucose model. Okay.
Yes, sir.
So the point is, let me share my screen. So Arjun, what I am going to do is to explain to you the glucose model. Okay. I have few more examples, but I would like others to be there. And I know that it was difficult for you to understand when you started this. Am I right? When you
Yes, sir.
when
Yes, sir.
you didn't understand. So with this background, what I have given, okay, let us say, let us see how much you are able to understand. The solution is the next step. I'm not going to go into the solution because there are ready-made packages. We'll get you that package, but let us see uh, whether you understand the governing equations. Once the governing equations are understood, the, the solution is not difficult. We know it. We can write, and also, I mean, we will also look at how the solution, and also interpretation is not very difficult. That also we know how to interpret it because you also know diabetes. Then we have to go into diabetes mellitus, and then what are all the issues and so on. Okay, so the first thing what I'm going to talk about is the model. How are we going to do the? How are we going to write down all the equations? Clear? Okay, so this is what I'm going to do. So I'll send you the paper uh, on which this whole thing is based. So what we are looking at is that uh, there is a, I mean, there's an intake. So there is an intake which is called as a meal uh, through the, I mean, it is either the oral. Okay, let's talk about OGTT. So then there is a gastrointestinal tract through which this meal goes through, and we have what is called as glucose appearance. Okay, RA. So that is the glucose appearance. So the glucose now, once it appears, we are going to see there is a again from meal to glucose appearance RA. We will see it a bit later how to convert it. Okay. Now let us assume that RA has come in, and I have the glucose system. So the glucose system, okay, I have various compartments. Okay, the glucose system, and in fact, there are two systems in this. There's a glucose system and an insulin system. So in the glucose system, there is a production system, that's the liver to the left, and an utilization system, which is the muscle, adipose tissue, and all that. Okay. So same thing, there is an insulin system, and to the left, there is a beta cell system, which is going to do the secretion, and then there is a degradation system. Okay, so this is what we have. Okay. Now we will go into the details of these systems and looking at this compartments. Compartment is a very powerful uh, technique, right? Differential equations for physiology, right? I mean, you may ask me a question: should I go to compartment? Yeah, if you are smart enough to directly from physiology, you can write. You can write, but this uh, compartments help us to keep track of what's happening. That's all. It is keeping track. Okay. So let us now look at the glucose system. So what are the things that are involved in glucose system? When I talk about glucose system, I have plasma glucose and the fast equilibrating tissue. So this is together, okay, one CP. Okay, this is actually one compartment, like thing. I'll come to this in a minute. In other words, I'm going to expand the glucose system. Are you able to hear me? Is everything okay?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay. So in the glucose system, I'm going to expand the glucose uh, into what's coming in, going out, and all that, and write down an equation. Okay. So of course, the glucose goes from here, and there is also a pattern to come back is to what is called as the slowly equilibrating tissues, okay, which are the muscle adipose tissues and all that, where there is an utilization of glucose. Okay. Now, glucose utilization is of two kinds. One is insulin independent glucose utilization, which is, for example, in CNS. It is insulin independent glucose utilization in physiology, in CNS. And then glucose dependent utilization, which I think they call it, here. So, insulin dependent glucose utilization, which is UID. Okay. So, insulin dependent glucose utilization takes place here, these things. Okay. And the glucose independent, of course, I just now said it is in the adipose tissue. In the CNS. Now, I have a number of other things. Volume. When I talk about concentration, I have to talk about volume. So, volume, distribution of volume of glucose becomes important. Most of these things are determined by tracer analysis. Then I have some rate parameters. I'll go into those details. And EGP, is the endogenous glucose production. Okay. And ET is renal extraction, happens if diabetes is involved, or can be zero if there is no diabetes. But anyway, we'll add that tomorrow. Now, how does it look like? Just I'm expanding this glucose system. I'm going to expand that. How does it look like? So the glucose system consists of two, I would say two things: glucose production and other things. And then where is it going? So actually the glucose system is this, but for clarity, we have put this as well. Okay. So the first equation I'm going to write. Arjun, you have to tell me whether you understand this, because this is the type of things which we will be doing.
Okay.
So now let's see, what is this? This is the rate of increase of glucose. Now, let us look at each one of them, right? We are going to look at each one of these things. Now, what is endogenous? So it's going to increase. So what is coming in? What is going out? So endogenous glucose production coming in, positive. Okay. Rate of appearance of the input glucose, plus. Then I have insulin independent utilization, UII, minus, because I'm getting it out. Okay. Then the utilization in the tissue, the rate at which it is being utilized, K1 into GP. Okay. Then there is always a feedback, and K2 into GT is what is coming in. So K1 and K2 are here. So the first equation is just a mass balance equation. Understood?
Yes, sir.
Okay. Now, so the next one, we have for the tissue. Okay. So the rate of increase of glucose in the tissue, dG by dt. Right? So there are two things in this. One is that there is glucose that is coming in due to insulin dependent utilization. Okay. And a, a few amount of glucose is also used independent of this insulin. This insulin need not push. There is an insulin sensitivity and insulin need not push. So there's a small amount of utilization even without this insulin dependent, which is called as K1 into G. Okay. And then, of course, this K2 is coming out, so there is minus K2. So again, balance. So from the physiology, I'm seeing the mechanism of glucose transport, okay, its utilization, okay, and the cycles that it goes through, and write down an equation. This is all. Is these two equations clear? We will have
Yes,
all
sir.
rate parameters, they are all K. Arjun?
Yes, sir. It's clear.
Okay. Now, so we always keep dividing to change the units uh, by the glucose, plasma glucose divided by Vg. Plasma glucose may be in mole, whatever, say, it may be P mole per kg and so on. So that converted into concentration. So you have that. Now, there is always a basal level in most of these enzyme kinetics, the hormone kinetics, and so on. There is always a basal level. Okay, all things happen above the basal. So the base. So in other words, all these equations are accompanied by a basal equation. Okay, so the basal equation, the basal endogenous glucose production is the sum of two things. One is the glucose, see that glucose utilization, okay, plus the renal extraction, which may be zero in ordinary cases. In diabetes cases, it may not be zero. So there's a basal. So this is physiology, that something is extracted if it happens to be that. So let us now look at the next one, insulin. Okay, I put it here. Right. So can you explain from this? So we are talking about insulin in the liver. This is liver. Okay. Now, M1 is the one which takes from the insulin produced in the liver to plasma. So I'm measuring plasma insulin, right? So, since I'm writing it in terms of I dot L, liver insulin, minus M1, okay? And we come to N3, that is hepatic extraction glucose. I'll come to that. So there is, you can see that here. I come to the physiology of it. Minus M1 into INT. So the first equation is emptying the insulin dabba box here. Plus, okay, M2 into I2P, and that is coming back from the plasmids. So these two things are I dot L. Plus, when there's a secretion, assuming that there is some secretion, I have to add that secretion. Yes. This one. Class level. So that is plus SO. Okay, that is the secretion. So again, mass balance. Now look at this. I have already got 3 equations here. Then I'm just keep adding equations, and all the equations are not very difficult to understand. They're simple and this thing. Say after I write and after I explain, I do this. Your job as researcher may be to actually write down this equation from physiology. But this is how compartment models work. There's a compartment, something is going out, something is coming in. Why it is going out? That physiology you have to understand. How much it's going out? There is a rate. Okay, and so is that clear?
Yes, sir. Yes.
Yeah. So now what is going out of the liver, okay, from the secretion and other things, is gained by the plasma, right? So this is the plasma glucose. Some amount is going back to the liver storage, which always happens. Some of them are going to the peripheral tissues. Immediately, this is what we called as equilibrating tissues. Okay, those two are going out, whereas from the liver we are getting in. So plus M1, 2 minuses, excuse me, I got. Clear?
Yes, sir.
Okay. So insulin concentration, when I talk about, because see, please note that everything depends upon the unit. Everything depends upon what is the unit. So M1 is 1 by, say, minute. This is the unit. Okay. So IP, there's plasma, insulin in plasma is P mole per kg. Usually concentration is expressed in terms of volume. And so VI is a distribution volume. That is VI is equal to kg liter per kg. Liter per kg. So if I now put IP divided by PI, then P mole per kg divided by liter per kg. So it becomes concentration I, which is P mole per liter. Clear?
Yes. Yes.
Okay. So there is also in literature on what is called as hepatic extraction. So hepatic extraction of insulin is defined by in 2 terms. So yeah, from the liver, some amount of actually insulin leaves irreversibly. That means that it's not going to come back, irreversible. And the ratio of HE, hepatic extraction, this comes, a lot of experimental work has been done. Hepatic extraction is M3, rate at which is going out, divided by M1 plus M3, total going out is compartment. M1 is going to the tissues, plasma. M3 is irreversibly going out. So HE, hepatic extraction, is M3 divided by M1 plus. Okay. This comes from physiology. In fact, I'll send you the paper and there is a reference to this. So HE is influx that leaves irreversibly to the total insulin leaving the liver, which is M1 plus. Okay. Now I rearrange the terms, then I can find out M3 is equal to HE into M1 1 minus HE into 1 minus HE. So from experiments, HE is found to be a linear, comes from a linear combination or from a linear relationship with secretion. He comes from a linear relationship secretion. So He is equal to minus M5 into ST plus M6. SFT is what secretion. Remember that secretion plus M6. So M6 is another constant that comes out, okay, because of this extraction. If I know M3 directly, I can put it, but more physiology says that it depends upon SFT as well as M6. Okay. So now whatever I have done so far during steady state, okay, should also be written at the basal state, from which actually we are jumping up. So at basal state, some amount of things are still going on. So all the equations I have written here is also reproduced. Okay, so this is actually rewritten in the where dB is degradation of basal degradation. What is going on? So at the basal level, both the secretion is equal to the degradation. In other words, what we are trying to say is that things don't shut down. There is some secretion, there is some degradation. Clear? I'll stop for a minute. Yes.
Yes, sir. It's clear.
Okay. Now, so what is that I have done? I have actually happily introduced M1, M2, M3, M4, M5, M6, HC, all those things. Okay. Now, I don't have a choice because I want to convert physiology into math. In which case, I'm introducing one after the other. In any physiology model, there are two things. One is called minimal model, and other is called maximal model. Now, so all these type of equations you know, there's nothing very difficult, right? All these equations. Now, the process of writing down detailed physiology, I've introduced a number of coefficients. I am moving towards a complex system where I'm taking into account every physiology that's happening. Okay. I feel this is the way I can explain actually a OGTT test. This model by which I'm explaining completely complicated fashion, complex fashion, with a number of parameters is called maximal. Suppose I leave out all these things. I just have the first two. And to a certain extent, it builds, and we'll see about minimum model. So, to a certain extent, it explain may not be very high because all physiology are playing. So, in which case, we will have what is called as minimal model. In diabetes, most famous minimal model called Bergman model. Very, very early model. Just talked about how insulin glucose system and fundamentally two lines. Okay. So these are the two things. Then now I have a number of things that has happened. Now I'm still going into subsystem. Let us look at what we mean by subsystem. I'm if you go back to my expressions, what is meant by subsystem? I have written one thing called endogenous glucose production. Okay, there is lot of again cellular physiology and other things. Endogenous glucose. I have to now so in any model I have to know every term clearly and meaning of the purpose. So what is EGPT? So there's exogenous. So endogenous. So now let us look at endogenous production. So there are a number of processes that are now we are going to we're going to look at one such process is endogenous glucose production. So what is endogenous glucose production? How do I write it? So again, the same thing. Something going out, something coming in. Okay. So the KP1 is the extrapolated endogenous uh, endogenous glucose production at zero glucose and insulin. When there is no glucose and insulin, this is what. That's the, in other words, nothing's there. This is the maximum that can happen. There is nothing there. We have endogenous glucose that is clear. Now, that glucose has to, that's the maximum. That glucose has to keep reducing. So there is a reduction, okay, due to what is called as glucose effectiveness, liver glucose effectiveness. Okay. So there is a reduction of this because it's not that I mean, this itself has to reduce because there's an effectiveness of the liver producing glucose. So this is what we call as liver glucose effectiveness. And the effectiveness depends upon the glucose present. Okay, so I'm reducing. So in other words, from KP1 ideal, I'm reducing to KP. Then there are reduction due to other things. Of course, due to the presence of insulin. Right? So there is an insulin signal that is generated because there's a delayed insulin. There's a, delay in that signal. So it's called delayed insulin. So the delayed insulin, which is going to be present with respect to time which may be delayed, is multiplied by the parameter that is governing the insulin action. So insulin is going to reduce now the EGP production, right? So there is a minus, right? And then there is what is called as portal insulin. The portal insulin also acts to reduce the EGP. So that is given by minus KP4, the rate at which it is going to. So you would notice that there is one ideal production EGP, and all these things are going to reduce. If there is a malfunction towards pathology, how would they affect? They would affect KP2, they would affect KP3, they will affect KP4. So that is why we are talking about digital twins as to what for a patient, what is KP2, KP3, KP4. And why are we modeling this? Tomorrow you want to treat, if I'm able to clearly find out, say for example, this portal vein, what is the sensitivity of this portal vein, how much is being contributed by the insulin in the portal vein, whether that is malfunctioning, which means the KP4 is very low, then we can go and look at the glucose production will go higher. Okay, so what is this delay? Okay, now here again, there is a basal level. Basal level is given by this. Now, the insulin, when it comes out and start acting here, actually it is coming out. We can model this as two compartments. Yeah. So you can see that from the beta cell, its secretion and so on. You can model this as two levels. One level in the first. So in other words, there is one level, and from which it comes to ID. I'm interested in ID because what is ID? Delayed insulin, which is available, okay, for me. So how much is the delay? That again is a matter of concern. Okay. So the delayed insulin is released, okay, from another company. It depends upon another company, which is the first compartment whose rate I1 is given by I1. So I1 depends upon and difference between in that compartment, the insulin level at that compartment, to the insulin, okay, the insulin that is that's available, okay, at that point of time, at that station, right? So that is I1T minus I gives the extra, okay, boost multiplied by Ki. Okay. So in other words, what is I? This is the plasma ions. So the rate of production of insulin, which we are looking at, first insulin is to be produced, but when it is produced and made available, there's a delay. So how is insulin produced? Insulin produced depends upon the rate at which it is produced, depends upon the difference between I1 and I. Okay, that's the plasma insulin, and I1 what is present at that point. Okay, so that so then the delayed insulin production, which is available for endogenous, that is also given by that kind of difference. Many times you will see that this kind of difference equations or differences are used, and here again, that's the difference. Okay, so Ki is that rate constant. Where we have seen, yeah, we have seen K1, K2, Kp. Then that is one process. Okay, the other process. Then another one or two equations. I'm just skipping it. In the paper, that would be. There is another process. Fortunately, there's a software called SAM2. It's about 80,000 software. That software will make your life very easy because you can just model it straight away in that to solve all this. And it is connected to MATLAB. So you need not worry. Since I'm writing an equation, I don't want you to worry like, oh, how am I going to solve it? Don't worry, you're not going to solve it. Simple step of code. You solve it. Your job is to write down these equations. Convert physiology into this. And if there is any experimental work that's required in order to understand this value.
Yes, sir.
Okay. So is it good so far? Understood?
Yes, sir. Yes.
Okay, Arjun, is it becoming easier after our class? That
Yes, sir.
so how?
Okay.
Yeah. Okay. So now our job is coming back to this. Yeah. So given a meal, how do I convert that meal into glucose appearance in plasma? That is my job. That's my next job. So that is another process. So in modeling, you have those kind of you have to separate it out into processes. Okay. Now, EGP, endogenous glucose production, is one process. Then glucose rate of appearance is another process. Why is it? So please note, you have to explain every equation. So I have an RA here. How am I going to get that RA is the next step. You can't say that I have eaten this much and that is directly converted into RA. No. So I have a set of equations. So the amount of glucose I've eaten, let's say that the glucose is in the stomach. And usually glucose, you can have it in the solid phase when you eat carbs or other things, and in the liquid phase, solid phase or liquid. So the total is the glucose in the stomach. Now, the glucose in the stomach, so the solid phase, one is solid phase. Because this K grinding is there, grinding will only come to solid. So that is the solid glucose, this is the liquid glucose. In fact, you can model anything with this. So the glucose actually that is getting converted, or in other words, rate of increase. Say there are dots here. First one does not have a dot. Second one has a dot. So Q dot Q1 is equal to K grinding. So the rate of grinding multiplied by, so when I grind it, convert it into liquid, my solid will come down. So minus K grinding into solid plus the glucose, which is directly ingested, okay, into the rate at which it is ingested. Okay. So that is, in other words, it is the glucose that is going in minus the glucose that is got. So in other words, you can say that the rate of increase of the solid glucose is one getting converted into liquid. That is the first term, plus what is coming in as a solid. That's the second term. So that's what. Again, only mass balance equations. We will go to other types of equations later, but this we will look at the mass balance equations. Okay, so that's done. If I now look at liquid, this is the second one. What I am grinding here, this first part, that should come as liquid. So that's an addition. Okay. So minus, so that is addition. Something has to go out, right? So that part which is getting empty, okay, is minus, in other words, gastric empty that's happening, getting into gut, say, for example. That is given by the first. So there's a minus and there's a plus. Now that minus, it's always like this. So you are now following the digestive system. Then this goes into the gut. So the gut, what is emptied here, becomes positive here. Minus intestinal absorption. So then the gut leaves out and then it goes to intestinal absorption. So RA is actually that intestinal absorption. that which is converted, a fraction f of which is converted, okay, is what is called as the RA which is going. So essentially, in that 5 equations, we have modeled how actually food products, it is absorbed within this. Okay. Is that clear?
Yes, sir.
Okay. So that's the next one. The third one is the glucose utilization. So up to this, now that I have absorbed it, RA I have absorbed it, then I have to look at glucose utilization. Those two terms, UII term and UID term. How am I going to write these two? So glucose utilization. Right? Glucose utilization, which is due to independent of insulin, II, independent of insulin, no big deal, because that well established norms are there, goes into utilization of the brain or central nervous system rather. That's straightforward polygraph. Okay. Brain. Things I think even the erythrocytes are some things which are big barrier. Then I have insulin dependent. This is insulin dependent utilization. So there's a kinetics too. So whenever I have kinetics, I go back to my friends. So it is a kinetic equation. And so I put down which is written okay, which we have seen. If you remember, we have seen this before, right? So so how does this remember how what is VM? Remember this? How would this curve be?
It asymptotically approaches.
Brilliant. That's it, right? So what is this
Yes,
value?
BBM.
PM value. Very good. Excellent. Excellent. So then the VM itself, okay, a function of X. That is the glucose present. Okay. So that you can, or sorry, insulin present. What we call as remote insulin. Remote. After all, it has to be insulin present because that's what we are looking at. So that can be given by a very linear equations. Insulin in the interstitial fluid. That can be given by a linear equation. Right? Then the next question you will ask me is, how does the insulin in the interstitial fluid will look at this? Enjoy the beauty of this whole thing. They are coming somewhere again and again and again and again and again coming. Okay. Now I am in the interstitial space. I can't say it's a constant. The insulin in the interstitial space also varies with time. So I should use what is called as an evolution equation. I know that I mentioned it. This is called as all these dot equations, all these equations are called as evolution equation. So this is an evolution equation. How is now the interstitial insulin? How is that varying? The rate at which interstitial, again, Same thing. Understood one, you understood everything. One is there is a decrease. Why? Because insulin is acting on glucose, peripheral glucose, utilization. Remember, we had that peripheral thing right there. First one. So we put it. Okay. From here, it is this peripheral. That's where it happens. So there is a peripheral utilization. And then there is, when there's a utilization, at the same time, there is also a production. Okay. That depends upon this. In utilization term, so I is what? Plus minus C. IB, all things are with respect to basal. That is a basal state. Okay. So that's what gives me the next slide. Now, I have the equations are complete. So the total glucose utilization. Now I know how what goes in. I know what is also this. Okay. Now, what are the other things that are still in limbo? As far as glucose thing is concerned, I've done this. Everything is finished, right? But I have to now come back to insulin. I'll just stop for a minute. I think I've talked a lot, but Arjun, Josan, or Bhagyam is there.
So, so the Michelin, the Menton equations, is it reflective of the receptor kinetics? Because the receptors get saturated, that's why.
Yeah, any kinetic equation has a saturation.
Yes. Oh, yes.
Okay, so it is Michaelis-Menten. This is standard.
Oh.
Okay.
And this can be used in any place that follows saturation kinetics.
Most saturation means you can use.
Yes.
Look, I've given you so many examples of Michaelis-Menten. Enzyme kinetics, 100%.
Yes.
Okay. So I want you to appreciate 2-3 things. One is how we have taken down, we have stripped it apart, the whole glucose kinetics, into so many steps, and how we have gone to one step to the other, and how hierarchically we have moved up to the interstitial space. Okay. And all of them are first order differential. Okay. But what I'm not going to cover in this course, which is quite advanced, is how to get this P2U, M1, M2, M3, and all. That is the problem. That I'm not going to cover because that will be too much for this course. But the idea here is, look, guys, it's not very difficult. Equations are actually simple. It's only mass balance. So in order to write mathematics, you have to know your physiology very, very well. Right? What, Arjun?
Yes.
That is more
yes,
important.
Definitely.
That is more important. The physiology, if you have understood, you will understand maths very easy. Okay. So now I have completed the all the glucose part of utilization. So now, what are the other things that are pending for me? The insulin. I happily put one secretion part. Okay. I have to now. There are two things in this. Oh, here is periphery. I was wondering where's somewhere. That's the periphery. The two things that are still remaining is the renal extraction. Okay. I have not come to that because I've done this normal. So that also I have to do. That's a very simple equation. Let's finish that. So the renal extraction part. Okay, so let's say that renal extraction through the kidney is very easily modeled as KE1. How do you think we can model it? Arjun, let's see. You know the physiology quite well. I know. I'm sure. How do you think you can write it? Just guess.
There should be a basal threshold beyond which only glucose is excreted in the kidney.
Fantastic, fantastic. So, what is that glucose? Some threshold. Okay.
It should be a
Fantastic.
difference equation. So
Brilliant,
minus.
Brilliant. What is the two minuses? I mean, what are the two terms in the minus term?
The plasma glucose minus
Minus
whatever the threshold.
some threshold. Absolutely brilliant. I'm so happy. Fantastic. So when does this hack? When this is positive, this whole thing is positive.
Yes.
Okay. So what happens otherwise? R is equal to 0. Right?
Yes. Yes.
So KE1 is the famous glomerular filtration rate. But K. Right? So there's a threshold. The threshold is K. Brilliant. Okay. So the only thing that is remaining for me is insulin secretion. Yeah, any questions? What is that insulin secretion? SFT. That's what I had written in the report. The number of papers on this. Okay. So insulin secretion. So what? Which is the one that's involved? What are the two organs which are involved? Liver, the pancreatic response. Right. So these are the two things that are. So I have two terms. First, there's a term called gamma. Okay. So I can say that gamma, which is a constant, okay, transfer rate between the portal vein and liver. Because your pancreas is involved, portal vein is involved, liver is involved. Okay. So these are the three things that are involved. So multiplied by portal vein is the fellow who's now going to give me. So I'm going to say, look at the compartment. On one hand, I have the insulin secretion. This is from the pancreas that is coming. Insulin secretion from the beta cells. So you see it here. From the beta cells, right? That's where it is coming. That's the insulin secretion. Now, so I have two compartments. One, the liver has to tell that, look, you have to produce this. Insulin has to secrete. So that comes through the portal vein. So this IPO, because that is the closest to, I'm going to write down as two steps. That is the IPO, is the portal insulin, IPO. And then I dot PO is equal to, of course, that has gone out. So gamma IPO plus what we call as SPO Okay. And SPO, function of T, is given by slightly complex expression K into G dot T plus SB for G dot greater than 0 is equal to y of T plus SB G dot less than 0. That G dot does not. So this is a separate paper for this. So K is the pancreatic response to glucose rate of change. And then we can have so many detailed parameters for this. So simple equation is given something like that. And so this completes the picture of all that you have in the whole of the two systems. Okay, so I've not
Yes,
included a few of them on basal levels and so on, but we can include all that. And now with this, I need to have values for, so the key is values. So every parameter, a normal value in type 2 diabetes, the K1, let's say K1, we had seen parameter K1. Beauty of this discipline is that the normal, if it is not 6.5, then for a type 2 diabetic patient, okay, it will be 0.04. Now, is this correct? Is this, it should be less? We can go back and look at it. Okay.
K1 is like the insulin sensitivity at tissue level.
Yeah, at the tissue level. So what does it mean? Glucose is being taken at the tissue, right? So if K1 is less, what does it mean?
The insulin resistance.
Insulin resistance part. So the tissue taking the glucose is going to be less. The rate of increase of glucose in the tissue is going to be less. Correct?
Yes, sir.
Right. So the K2 is, for example, is interestingly is almost similar. Not 7.9. That also is slightly even less. Okay. So this is, if it is more, then more will be taken and less. There's a minus sign there. Okay. But it so happens that K2 is almost the same, not 7.9, not 7.1 between the two. So each one of these parameters, we can see that I'll send you the paper. You see that they are different. Now, the key here is to actually evaluate these parameters. And that's a different topic, as I told you. And that is the curve fitting parameter estimation. There's a curve that's called parameter estimation. So next time when we do data analysis, parameter estimation, we will do it as a part. In fact, people don't understand that unless you have a physiological model, data analysis has no meaning. This only gives you into that database design directly. The physiology part of it comes this kind of equations. Clear?
Yes, sir.
Okay, so that's the first thing. Just stopping it. Plural there only. Dr. Bhagyam, you've been listening. Is this part of
No,
it?
I didn't. I mean, see, what I understood from here is that when you have an equation, you break everything into a compartment and resolve it by that compartment using the basic physiology. The parameters will change depending on the disease, whether you have insulin resistance or anything like that. That
Exactly.
much I
Yeah.
was clear about it.
Yeah.
I understood that much, but yeah.
So the other thing is all equations are only mass transfer. That's all.
Okay.
That's all. We are looking at only mass transfer. Okay.
Okay.
I want to do something on cardiology, but I think Dr. Sundar is just now messaged me that he's an emergency case he was on. So I'll just postpone it, guys, to when he comes. I want to do it when he's around. So we will do that the next class. Okay. So this stop here, and I will do the other one in the next class. Because how the simple mathematics is very useful in cardiac cardiology and cardiac physiology. I'll do that in a minute. Right. There are a few other equations which we will go into detail. So this is just a step that how physiology is converted. Okay.
Okay.
Great.
Yes.
Great, Arjun. I'm very happy that you have really understood a lot of things. Joseph, you are with me?
Yes, sir. Yes, sir.
No problem. Yeah. Okay. Great.
Thank you, sir. Happy New
Thank
Year.
you. Thank you. Happy New Year. Thank you.
Happy New
Right.
Year.
So,
Happy New Year, ma'am.
Happy New Year, sir.
so at least with this course, you feel you've gained to understand this. Okay.
Yes,
So
Yes, sir.
definitely, sir.
Yes.
great. Okay. Thanks. I'll send this paper. You please read the paper. Okay.
Yes,
Yes, sir.
thank you.
Anything we
Thanks.
can discuss.
Yes, sir.
Bye.
Thank you.
Thanks, Dr. Bhagan. Thanks.